starting with the great name of Almighty Allah, who is the most gracious and most beneficent. So the topic on which I am going to demonstrate my presentation is soil-water crop relationship. So what the soil is made up of? The soil is made up of following constituents which make up the soil. Those are mineral materials like sand, clay and silt, organic matter, water and air. These constituents make up the soil. Now here we will get to know that what part of the soil make up about how much percentage, means like mineral materials are about 45% present in the soil, and 5% organic material, water 30% and air 20%. So these are the different proportions of the soil constituents. Now mineral components. Mineral components, except in the case of organic soils, most of the soil solids frame up consist of the mineral particles, means that the major portion of the soil is composed of the mineral particles, and mineral particles are the sand, clay and the silts. The composition of the mineral particles will further define whether classify the soil, that whether that is the sandy soil, clayey soil, silty soil. Second point is they are variable in size and composition. They can vary from the small rock particles to the colloids. Means there can be a different variations in the size and composition of the minerals. Like if I say that the soil is a sandy soil, that means the major portion or the greater or the more than the 50% portion of the soil is covered by the sand. And if I say that soil is the silty soil, then the more than 50% silt is present in the soil. So this is how they varies in the size and composition and can also be classified. Then third point is the mineral can be raw quartz or other primary materials, coarser fraction which have not changed from the parent material. Means the mineral composition can also includes those materials or those fractions which are coarser and have not changed from the parent material. Means have not get breakdown into the small sediments. They can also exist in the mineral composition. Then fourth point is they can also be silicate clays, iron oxide formed from the breakdown and weathering of the less resistant minerals, a soil formation process. These are called secondary minerals. Secondary minerals are those minerals which are formed after the breakdown of the parent materials, such as silicate clays and iron oxides are formed. Now another term that is mentioned here is the weathering. Weathering means the under the action of the environment such as rain, sun, wind, the breakdown of the rocks into the small sediments are known as the weathering action, because of which the secondary minerals are formed. Now coming towards the classification. The classification of the soil on the basis of USDA and ISS. So this is the classification on the basis of the United States Department of Agriculture and International Society of the Soil. Now on the basis of the size, these are the constituents which make up the composition of minerals are classified. One is the rock, sand, silt and clay. So the size which is greater than 2 mm can be called as rock. The size of the particles which varies from 0.05 to 2 mm will be called as sand, and size from 0.002 to 0.05 mm will be called as silt, and then less than the 0.002 mm will be called as clay. So these are based on these are classified according to their sizes. Now coming towards the sand components. When we see the sand, they vary in the size and we can easily see them with the naked eye, the particles of the sand. And whenever we take the sand in our hands and rub between our fingers, they feels like a gritty. Gritty means a powdery, gravelly texture that we feels like in Sindhi we can say when we take the wari in our hands, that feels like a gravelly, gives us a gravelly texture, and that is basically the sand feels that we feels that is the sand. Actually the sand particles do not adhere to one another and are therefore not sticky. Sand particles have less force of attraction between the particles, because of which they do not stick together and do not adhere together. They don't have the adhere property. Now coming towards the silt and clay components. Silt particles are smaller than sand. The silt particles are too small to be seen without a microscope. It feels smooth but not sticky even when weighed. Silt particles are basically smaller than sand and we cannot see them with the naked eye but with the help of the microscope, and they do not they feels like a smoother when we touch it and in within our fingers. They feels like a smoother but not sticky even the weight. Even when amount of water is added, they don't feel sticky, but they feels like a smoother, gives a smoother texture. Then there's a clay. Clays are the smallest class of the mineral particles. They adhere together to form a sticky mass when wet and form hard clods when dry. Whenever we add a water, they feels get wetted and they forms, and the different small particles combine together and form the clots, and on drying they become hard clots. So that's what the clay is. Now coming toward the colloidal materials. Basically, the colloidal materials are the materials which are if I talk about medium that is liquid, then they will be suspended in it. They will not settle in the bottom, but they will be suspended in the water and will collide with each other. This now what is their size? The smaller particles less than 0.001 millimeter of the clay and similar sized organic particles have colloidal properties. Means those clay particles which are less than 0.001 millimeter can have the property of the collision property. And again, if I talk about organic particles, if they will again have the size less than 0.001 millimeter, then again they will have the colloidal properties and can be called as colloidal materials. These particles can be seen with an electronic microscope. Means again we cannot see them with the naked eye but with the help of the microscope. The colloidal particles have a large area per unit weight. As we know, more the finer they are, more the surface area the particles have. So there are enough surface charges to which the water and ions can be attracted. Means their ions are within the water and can attract it. These charges makes them adhere together. Because they are consist of charges in the water, they even attract each other. Now there is a humus improves the point is there, the humus improves the water holding capacity. Now basically the humus is the hard organic material that forms in a soil when plant and animal matter decays. This because of which humus improves the property, that is the water holding capacity of the soil, by reducing their pores between the soils. Water holding capacity of the soil is that how much the soil can retain water. Now coming towards the soil water. The quantity of water in the soil is determined by its moisture content does not give a true indication of the soil wetness. Means it means that the quantity of the water present in the soil cannot be measured in terms of the moisture content. Now second point is telling us that the soil, a clay soil, which on handling feels dry, can be at the same moisture content as a sandy soil which feels wet. Now here the comparison is shown between the clay soil and the sandy soil, that at the same moisture content, means in the clay soil and sandy soil there is the same moisture content, but the clay feels dry and the sandy soil feels wet. Why? Because if we see that the clay soil are the smallest particles, because of which they have the very small pores in between them, and it has lesser infiltration capacity and less yielding, but has greater water holding capacity. So three things I told you, that one, that it has the less porous, clay soils are the less porous, and secondly they have the less infiltration capacity, but third is that they have the greater water retention, means greater water holding capacity than the sandy soil. And in sandy soil is in contrast, then they can infiltrate quickly because they have their pores are greater as compared to clay soil. Then again sandy soil has the infiltration capacity is greater, but water holding capacity is less, because of which with the small amount of water they starts to feel weight. But at the same time, if we see at the clay soil, they don't feels weight too quickly, they feels dry. Now coming towards the third point, a plant will have less difficulty extracting water from a sandy soil than from a clay soil at the same moisture content. Why? Because they have the small, the small portion, small clay soil is small, less porous as compared to sandy soil, because of which plant will have to plants will be at stress at the sucking the water from the clay soil as compared to the sandy soil. And third point is there is need for a soil wetness, which reflects the ease or difficulty of the extraction of the water from soil by the plants. Now wetness of the soil, when we wet the soil, either the soil gets easily water, either the plants get easily extract water from the soil, or gets becomes difficult for the plant to extract the water. So means that the plant can either have to work hard for that, or work less than in that case in which the water is easily available. So the concept of the soil water potential is therefore used in the soil, plant and water relationship. Means if we want to measure or determine the wetness, or the extent that how whether the soil will be easy to extract the water or not, that will be measured from the soil water potential. So soil water potential is defined as the amount of work that must be done per unit quantity of water to transport. So that is basically the work per unit quantity of the water that to transport. So now coming towards the next slide. Mechanism of the soil water movement. The mechanism of the soil water movement means what is the mechanism that how this the water present in the soil flows or moves. The flow of the water in any hydraulic system, including the soil plant water system, takes place from a state of higher to one of the lower potential. Means whether that is the hydraulic system or soil plant water system, the water flows from the higher potential energy to the lower potential energy. Why? Because whenever I talk about that, that is the higher potential energy, the potential energy depends on the height. If the great height would be there, potential energy will be greater, and at the from the greater height to the lower height, the water easily travels, because of which we said that the water flows from the state of the higher to the lower, because the at the highest at the greater height there will be the higher potential energy, and at the less head or less height there will be lower potential energy. Second point is the steepness of the potential gradient from one point in the system reflects the ease with which the water will flow down the potential gradient between the points. This means that the steepness means slope. If a surface is slopy, then there is a difference between, means there is a difference between the potential energies between 2 points, then water starts to flow. That's simply that points is trying to say. Then the third is that soil water system is made up of 3 components. Coming towards the next slides. Number 1 is the gravitational potential, means these 3 are the components of the potential. Number 1 is the gravitational potential. Number 2 is the pressure potential. Number 3 is the osmotic potential. The gravitational potential means due to the gravity force, the soil water starts to move. That would be called as gravitational potential. And second is the pressure potential. This is positive when greater than atmospheric pressure, and negative when below atmospheric pressure. Means whenever the pressure of the potential pressure is the greater than the atmospheric pressure, then that would be positive. If less than atmospheric pressure, then that would be concluded as negative. The atmospheric pressure is about 14.69 lbs per square inch, and if we will simply say that if it would be greater than 14.69 lb per square inch, then it would be positive. If lesser than that, then that would be negative pressure. A negative pressure potential or tension or suction is also known as metric potential. Means we can also say that the negative pressure can be said as tension or suction or metric potential. And the point at which there is a negative pressure, or then the water then there will be a suction, and because of which water will starts to flow. It is characteristic of a soil water above a free water surface. Now third is the osmotic potential. Osmotic potential occurs when there is solutes present in the solutes in this present in the soil tends to move the water to the higher concentration of the soil solutes. So that's because of this process the water starts to move either in the the semi-permeable membrane. Means if the soil is semi-permeable, means allows the water to some extent, then the solutes will help to move the water, and the water will starts to flow. That's what the osmotic potential is called. Now sum of these 3, gravitational potential, pressure potential and osmotic potential, will be called as the total potential of the soil water, neglecting kinetic energy. Why? Because water in the soil moves very slowly, because of which we neglect or we ignore the kinetic energy. Now coming towards the classes of the soil water. Water present in the soil may be classified under 3 heads. Number 1 is the hydroscopic water, second is capillary water, and third is the gravitational water. Now as you can see the hygroscopic water, when an oven dry sample is kept open in the atmosphere, it absorbs some amount of water from the atmosphere. This is known as hydroscopic water. Means when the oven dried
sample of the soil is open in the atmosphere and that absorbs the water from the atmosphere, that would be known as the hydroscopic water. Now, one thing should be kept in the mind that the hydroscopic water is not available for the plants. Those are just available to be absorbed by the soil and soil solutes. Otherwise, that is not available for the plant suction. Then second point is the capillary water. Second is classification is this capillary water. Capillary water is that part in the excessive of the hydroscopic water which exists in the pore spaces of the soil by molecular attraction. Means water that is when the soil gets the absorbs more water from the atmosphere and that water existed in the soil would be called as capillary water, and that will tries to rise in the soil and will with the capillary action, and that will be called as capillary water. As in the right side you can see that at the it is mentioned at the bottom that oven dried, one second, at the bottom is mentioned the oven dried soil, and that is present in this mention the oven dried soil and that is present in the atmosphere. Then a portion is mentioned that is the hydroscopic water, and at the left side it is written it is unavailable for the water, that is not for the plants. Then there is the wilting coefficient. Wilting point is that point at which there is there is very less water for the suction for the plants and suction of the plants. Then there is a point that is coming available water, means this capillary water is available for the plants, means that is coming in the portion of the available water. Then third is the gravitational water. Gravitational water is that part in the excess of the hydroscopic and capillary water which will move out of the soil if favorable drainage is provided. Means that that is the water which in the form of the free drainage that is the excessive water other than the hydroscopic and capillary water that flows over the surface due to the gravitational action, that is known as the gravitational water, and that is also known as the superfluous water. Now coming towards the next slide, the available water in the soil. Now at the bottom you can see there is no water available when the soil is oven dried. At the point of the wilting you can see there is 0% available water, but when we start to move a little higher than the wilting point we can see that is the little reserve available and plants stressed. Means if we say that the plant's roots are coming up to the 25% in the area of the wilting point, then that would be all right, but not much, because otherwise otherwise plants will be at stress to get or to extract the water. So it would be all right if we come up to this point, means 25%, but not more than that. Otherwise soil will become will start to wilt and will decay and get dried. Then here you can see from the wilting point up to the field capacity, that is the total available water, but from the topmost point of the wilting point up to the field capacity, that is the readily available point, readily available water. Now field capacity is defined as the maximum water holding capacity of the soil after free drainage, and that is the because of which we can say that is there is the 100% available water, and after which we can say saturated and excessive water. In this point all the pores of the water will be filled with all the pores of the soil will be filled with the water, whether there is the micro or macro pores, both will be filled with the water, but in the field capacity, all the small pores of the soil will be completely filled, and the large pores will be partially filled with the air and partially with the water. That's how this diagram describes that how the water is available in the soil on the basis of these parameters, that is the wilting point, readily available water, field capacity, saturated. Now coming towards the next slide. Availability of the soil water. Soil moisture is always being subjected to the pressure gradients and vapor pressure differences that causes it to move. Certain moisture contents are of the particular significance, often called soil moisture constants. Those constants which we have discussed previous are certain that is what it is talking about, that certain moisture contents are of particular significance are important. Those are also called as soil moisture constants that we have discussed, these: wilting point, field capacity, saturation point. With regarding to the irrigation and agriculture engineering, with respect to irrigation and agriculture engineering. Now coming towards the saturation capacity, that what the saturation capacity is. When all the pores of the soils are filled with the water, the soil is said to be under saturation capacity or maximum water holding capacity. The tension of the water at saturated capacity is almost zero, and it is equal to the free surface water. It is the saturation, it's clear that the all pores of the soil is going to be 100% filled with the water. Then there field capacity. The field capacity of the soil is the moisture content after the drainage of the gravitational water has become very slow and moisture content has become relatively stable. This situation usually exists for the 1 to 3 days after the soil has been thoroughly wetted by rain or irrigation. When we will irrigate the soil, then after 1 to 3 days it will become wetted and the field capacity will be achieved. Field capacity is simply the maximum water holding capacity of the soil after free drainage or against free drainage, when the drainage has become very low. At field capacity, the large soil pores are filled with air. Okay, it's written that the large soil pores are filled with air and the micropores are filled with water, and any further drainage is slow. This field capacity is the upper limit of the available moisture range in soil moisture and plants relationship. Now coming towards the next slide. Moisture equivalent. Moisture equivalent, this is an artificial moisture property, means it's an artificial property of the soil and used as an index of the natural properties. Index means number of the natural properties. It is the percentage of the moisture retained in a small sample of a wet soil in 1 centimeter deep when subjected to a centrifugal force 1000 times as great as gravity, usually a period of the 30 minutes. Okay, it's telling us that if we take a sample of the soil 1 centimeter deep and we weight it, and against the gravity, means against the gravity what the water it retains, that would be actually the moisture, that would be the moisture retained by it, and in for the period of the 30 minutes, that retained moisture will be called as the moisture equivalent. And why it is roughly equals to the field capacity? Because moisture equivalent is also the water retained in the soil the gravity, and field capacity is again the water retained by the soil against the gravity. So both have this link, because of which they are roughly equals to each other, but there is an specifically defined like 1 centimeter deep, and it is against and subjected to the centrifugal force 100 times as greater as gravity, subjected to this force, and for the period of the 30 minutes. If we will get to know the field capacity, we will be even with these relation can find permanent wilting point and hygroscopic coefficient. How? Because the moisture equivalent is also equals to 1.8 to 2 times the permanent wilting point, and moisture equivalent is equals to 2.7 times the hygroscopic coefficient. Now another details are written that moisture equivalent is used as a single factor to which the properties of soil can be related within reasonable limits. Means these are those constants or limits with which the moisture equivalent have relationship with the permanent wilting point, field capacity, and hygroscopic coefficient.